Just to make sure we're all on the same page. The firmware is the piece of software which is running in the most privileged level, which has access to the hardware. If you're talking about like a system firmware, it may have an access to entire hardware and make capabilities to brick a system or implant the system, make it stealth and persistent implants if you compromise the firmware. In the modern system, x86 system, typical attack flow looks like this. So there is a remote code execution when the attacker executes the code in the context of the some processes. Then it makes local privilege escalation to get the root or the kernel privileges. And then the next step can be, you may want to hide yourself in an OS level. You can modify some OS files. Or you can try to own the firmware and try to hide itself in the firmware. Why this is important? Because when you own the firmware, you can persistently be there even if you reinstall operating system, even if someone changed the hard drive, and also it makes you also stealthier because it will be not visible from the operation system at all. So that was sort of the motivation of the talk. Now let me try to switch to the presenting mode. Great. Another couple of words about motivation. Usually when you need to investigate the system, you need to real access to the system. But then you, as I mentioned, want to run the test across over all of the instances, and then how you can do that. So that was what we asked ourselves when we started this research. In the end, we will see that there is possible to make an investigation based on the firmware updates images. So when the vendor releases firmware updates, you can run some static analysis, or even less heavier than static analysis, some sort of heuristics based on some signatures, and you can find the specific instances of vulnerability in that specific images during the update. So you will see that the new update will come up with the new vulnerabilities, or old vulnerabilities which didn't patch it previously. So a little bit about UEFI-based firmware. When I mentioned about UEFI, I mean system firmware, or also call it BIOS. It's all the same. So where it's stored? It's stored in a SPI controller, which is connected over SPI bus to the PCH in a typical x86 system. I will call SPI for the future, but it's not SPI with the Y in the end. It will be SPI with the I in the end, so SPI. Just to make sure that it's clear that I'm not talking about spies. So the firmware living in a SPI controller and special flash memory, which can be 8 or 16 megabytes. And in this memory, there is a bunch of things which are stored, including the system firmware. This storage is used for the firmware for a specific reason, because when the system is booting up, the memory and the hard drive is not initialized yet. So you need to run the code from some storage which is not memory and not hard drive. And there's a special mechanism which is allowing to run the firmware from the SPI when it fetches a reset vector directly from the SPI, from the specific physical address. And this SPI chip, which is basically, as I mentioned, can be 8 or 16 or 32 megs, should have some protections, because it's not supposed to be accessible from the ring 0. Because if you can access from the ring 0 SPI content, then you can override entire SPI, break your system, or install your malicious code in the BIOS. So the SPI controller has the regions. The regions is basically the logical blocks of the SPI controller. The minimum logical block is 4 kilobyte. So first logical block is flash descriptor, which will be the main sort of object for the discussion for today. It also call it SPI descriptor. I will call it SPI descriptor. So the second region is the BIOS or system firmware region. Then there is Intel ME region. There is also GBE region, Gigabit Ethernet controller configuration. And there can be a couple more, even embedded controller region can be there. So some of this region may have different protections. For example, a BIOS region should have special protection, which is called BIOS control register protection, which supposed to mitigate all of the attacks from direct access to this region. So if someone tried to, from the software, send transactions to this memory over MMIO of SPI controller, that's the way how software communicate to the SPI memory, SPI controller over the SPI controller MMIO region. That's the special memory which allows software to communicate to the different devices, including this one. So when someone using the SPI controller MMIO region send the right transaction to the BIOS region, it's supposed to be dropped by the BIOS control register protection. So that's how does the BIOS should protect the BIOS vendor should protect the BIOS. Also, there's another protection called PR registers, which is allowing in a level of SPI controller set permissions, which region should be accessible or not. But these PR registers may cover any region. They can be applicable not just for BIOS region. And there's another protection, which I will explain a little bit later, in the level of the SPI descriptor, or flash descriptor. Let's go deep a little bit. So SPI descriptor, another name is flash descriptor, stored in a region with index 0, so first region. It's 4 kilobyte, and this 4 kilobyte is basically has a specific format and it has the specific things inside it. So basically, first it defines all of the other regions, layout of all of the other regions. So basically, SPI descriptor is telling sort of here is this specific region, here is this specific region. And this is sort of important because when software needs to communicate, or even BIOS need to communicate to different components, it knows where is the exact location of the BIOS, it knows where is the exact location for other regions. Then it's also, as I've already mentioned, storing something which is called an access control table. Access control table is the table for the permission who can modify the content of the different regions. This protection is applicable after all of the rest protection is mitigated or not mitigated the transaction. So when transaction go into the SPI memory, it first checks for BIOS control register, then it checks for PR registers, and then if they are not set, then this protection is checks if the transaction should go on or should drop and not have permissions to run. Why it's still important, a really important protection? Because BIOS control register covering only BIOS region. So basically all of the rest regions should be protected by this access control table, including the SPI descriptor itself, because SPI descriptor is one of the region. So the SPI descriptor contains this table. So if the SPI descriptor by mistake allows software override itself, then software can override this table and open the access to other region. For example, read or write to a ME region, or read or write GBE region. GB is a Gigabit controller configuration. ME is manageability engine region. Some of this region is more documented, some of this region is less documented. But for BIOS region has really good documentation because the format of the BIOS is the standard, and you have a bunch of tools which you can run to decode the BIOS region. ME region is a little bit documented, but mostly reverse engineered, and there is also a bunch of tools which you can use to take a look inside ME region. GB region doesn't have much documentation, but it has at least some documentation when you can check where's the MAC address is stored. MAC address of the Gigabit Ethernet controller integrated in the motherboard, supposed to be stored in GB region. Okay, coming back to this SPI descriptor or flash descriptor. So this master control table is highly important because it's responsible to protect the flash descriptor itself and another region for read access, for example, ME region, because a typical system is not allowing you even read ME region, and the SPI descriptor is responsible for this. Another really important feature for the firmware is the firmware update. When the BIOS vendor want to deliver fixes for the security of functional vulnerabilities, they need to have a secure way to deliver update. And the secure way to deliver update is sort of documented right now, although it's not a standard, but it's almost a standard. But according to my knowledge, it's still not a standard, but it has really well documented spec. It's called capsule update. So basically, it's the method when you can standard, more or less in standard way, say, okay, I want this BIOS update will be delivered. This is and one difference between this and like just any regular updates, which you can see that the tool which is supposed to run update is part of the package. So when this capsule update is delivering, the tool which is running update is part of this capsule. So it's not just a data which you want to replace, it's also the tool which is running to replace it. A really important part. One another important part is this capsule update is running during the boot or upon the sleep state. Why? Because during the boot, the device is not initialized yet, and no one can send a DMA transaction and overwrite the content of the new update which is happening. Basically, running during the boot is allowing you running in much more secure state than running during the runtime. But there is one mistake, there's a couple of mistakes which is vendor typically makes. So first is they try to create this update mechanism at runtime because it's sort of better for usability. This opens two issues here. One is during runtime, malicious device which has DMA capabilities like USB-C dongles or other PCIe devices can overwrite the memory of the update after it checks, but before it starts updating the BIOS. So sort of race condition vulnerability. Another problem is that the BIOS update is not really fast. It took between 30 seconds and 2 minutes. Because it takes so long, BIOS vendor, they split this process to couple steps. And between these steps, they usually didn't enable protection back. So when they deliver an update, they disable protection for the BIOS region, but then they didn't enable it back until the last step came. So if some ring 0 code run between these steps, it could just override BIOS directly without zero protection. That's another vector which is typically we see in some of the BIOS update mechanisms. Another thing is that flash descriptor should be always read-only. That table, which I was mentioned in a slide before, should always protect the descriptor itself. Descriptor should be read-only, and just during the manufacturing phase, the descriptor should be modified. So, how to check these vulnerabilities? At least the basic one, which we explained it in a couple slides before. You get a system, then you run different tool to check configuration. You run different tool to update your BIOS, and you sort of investigate it, how does it go? Is it checking signature? Is it going over runtime? Is it going over boot time? Then you run chipsec to check configuration, and so on. When you have a system, it's pretty easy to find, and there is a bunch of examples from the industry which we see that the people just run the tools, find the vulnerability immediately, which allow you to implant system. But let's think about how we can apply the same theory, but to find vulnerability before in a way only based on the image without system, before this image even will be delivered to the system over update. So this is not the first work in this area. There was also work in 2014 by Teddy Reed, who made the first sort of scale analysis of the UEFI firmware. So we take a look on that and also reuse some of the materials. And there is a bunch of tools which you can use to decode the UEFI-based firmware. So that's also not new. So you can just run it and see each component from the UEFI-based firmware which you read it from the SPI memory, and you can make a forensic on them. You can put the whitelist for them. So it's not a completely new area. So there is something which we started from. So in our theory, we have 2 steps which we need to do to build the final algorithm to identify the vulnerable images. So first step is easy automate. We basically need to download all of the images from all of the vendors' website. Then we need to check which one of them is not signed, and which one of them has full ROM image, full SPI ROM dump, and which one of them has specific characteristics or specific fields in a SPI descriptor. That's pretty simple steps. And when we run it automatically for all of our images, we can get some statistics out of that. But then it will be next step, which is hard to automate. We need to actually verify this theory, verify this algorithm, figure out false positives, false negatives, so on. There's second step, run in a system and check what did you find, is it correct or not. So what we're looking for. As I already mentioned, we're looking for unsigned image. What this mean? It means that someone can modify the image and flash with the malicious BIOS or using the classical the vendor's update tool. So basically, vendors deliver update tool. Attacker can grab this tool, can modify the image, and flash this image to the BIOS. Second is because this image is unsigned, and we make some assumption that if there's not a real capsule, then it probably delivered over runtime. If it delivered over runtime, then the BIOS control register is also not configured correctly. And then because we will find specific characteristics in a flash descriptor, then we also assume that the flash descriptor is not protecting. So that's 3 vulnerability we try to detect in each system which we analyze it. Okay, so we built sort of a pipeline to get the good candidates to run our algorithm. So when we download all of them firmware updates, we figure out that they all have different formats. They all have different they package it differently, and so on. So first step, we need to extract BIOS update from the firmware package update. So from the package update, it's not the BIOS update. Firmware package update contains the BIOS update plus tools and plus some extra information. So, but we need that BIOS update image to run our analysis. And then we run our analysis already for that images. So that's our initial set. We have almost 33K firmware update packages. from 9 vendors. It's not full set. I believe it can be much more. We didn't download every single BIOS update package. We just downloaded the one which is easy to download. So we got 44 candidates. Candidates meaning that we believe it is a firmware, but we are not sure. And then we run the analysis, and then we detect if this really UEFI-based firmware or not. So we detected more than 21K of the unique UEFI firmware images. You might ask, what is the rest? What is the almost 20K images is? So we believe it is legacy images or images which we don't know format, and we couldn't decode them. So as already mentioned, that vendor firmware package updates is not equal to the UEFI image or UEFI update image. So when we start investigating deep, we find there is a bunch of interesting things there. For example, tools which is vendor providing to update the BIOS, in many cases contain the driver, signed driver, which has a really easy ways to make a privilege escalation because it has the IOCTLs like read-write physical memory, read-write MSRs, and so on. So the tools which is vendor distributing, they are especially interesting for the future research as well. But these tools is also interesting for us because when we will verify our theory, we need to run these tools to double check that the vulnerability which we detected is confirmed. So then another steps when you got the firmware update package, you can run a bunch of tools to extract the BIOS update. I will not stay long in this slide, but there is a bunch of different methods, vendor-specific, not vendor-specific, which you can use iteratively to extract the BIOS update image from the update package. Basically, the package which is BIOS, which is platform vendor delivering, like Lenovo, ASUS, HP, and so on. Okay, so we extracted all of the firmware update packages. Then from them, we get all of the BIOS update images. These BIOS update images, we already pre-sorted, and we know some of them is UEFI BIOS update images, and we know the list. Now we need to really precisely create the algorithm which will detect the vulnerability. So first we need to exclude the known UEFI capsule images, because capsule images typically sign it and typically doesn't have as many problems as others. So then we need to have the image which has exact size, because if it has exact size, it has flash descriptor in it, because flash descriptor is part of the size of the flash memory. Then we need to make sure that the SPI descriptor is sitting in offset 0. So it's really valid SPI descriptor with offset 0. And then we need to make sure that the SPI descriptor is not protecting itself. So practically speaking, we're looking for images which is exact size to the SPI flash memory, which has in a decoded format, in a chipset decoded format, which has the reserved bit and the signature, which is indicate that this is valid SPI descriptor, and in permission access table, it has here read-write. This read-write indicates that CPU can override the flash. In the terminology of the SPI controller, there is something which is called master. Master is, in a SPI bus, someone who can send a transaction. And CPU in this terminology is just ring 0. So basically, if CPU has access to the SPI descriptors, meaning that ring 0 attacker or anyone with ring 0 privileges has the access to the flash descriptor. That's what we are looking for. Plus the rest heuristics. So our initial analysis giving us 3,500 images, which is matched to this heuristic. So this is our suspects. So this is our candidates to be a vulnerable image, which will in the BIOS update packages. So this theory is not perfect. It has false positive and false negative. False positive is that not all update packages that contain full spy image correspond to these vulnerabilities. In some cases, BIOS can be protected at least for the 2 out of 3 vulnerabilities, but still will not be signed. So this is something which we sort of not splitting here. Another thing is if the BIOS update delivering over USB, it requires user interaction, and it may be a way how does vendor is building protection with the user interaction sort of requirements. Another one is even if you detect the SPI image with these characteristics, during the update mechanism may skip spy descriptor at all. This is sort of the way how some vendors implement this. So they basically deliver an update, but during the delivery update, they just skip in part of the image. They know that this already was flashed during the manufacturing phase and not do it again in the next steps. Of course, we have false negatives. One of false negative is that even there is a signed capsule update, there still can be vulnerable to the rest vulnerabilities like a descriptor and BIOS control register is not protected. Also, we excluded read-only flash descriptors in our heuristics, which we minimize the number of images, but it's not really good because if we excluded that, we may miss to another vulnerability in the same image. So because we combine all of them, we sort of may miss the image which has 2 out of 3 of them. And some of the capsule they may not be signed, and we also did not detect in this. Okay, after we make a manual analysis and verify all of the images which we collected and verify some of them manually by checking in a system, we got the conclusion that more than 500 models have the vulnerable BIOS update images. Most of them is MSI and Gigabyte. There is also ASRock and ASUS, which has a bunch of them, and some vendor just may miss some platform to deliver the proper update mechanism. So let's go over some of the examples. MSI, almost all of the system is vulnerable. We verified in one of the example in one of the system. Then, there is just how we manually check it. We check the image, the characteristics of the flash descriptor, as I already mentioned. You can check it manually or over chipsec. And also, interestingly, that some description in a vendor website also can you give idea. So some of the vendors in the description of the update package explaining how they're delivering this update package, and based on this you already can detect if the system is vulnerable or not. Because if the vendor is telling that they deliver an update during runtime, that's already awesome. It's already a good indication that it's probably a vulnerable system. Gigabyte, the same problem. All of the 3 vulnerabilities detected in almost all of the images which we had checked. Dell has interesting results. So some of the system is still vulnerable. So we analyzed 78 images, and out of that 51 is vulnerable. That's the example how we will verify. We just buy the system, run a test, and check, okay, yeah, that's BIOS is open. Our heuristics is correct. Then Lenovo, as you see here, also when we run the update tools, it going over runtime. It didn't check any signature. It has the unsigned image. Also verified that it has some models, 26 models of the BIOSes, which is vulnerable. HP, we verified 11, which has vulnerable package updates for the 6 models, but HP has a high rate of false positive. As you can see here, our assumption doesn't work because it has a sort of, it checks the signature with some manifest which is delivered separately from the image. So that's why we didn't detect this. So in HP we have high rate of false positive. ASUS, it doesn't have false positive, although it didn't correctly detect the one of the vulnerabilities. So the most modern images for ASUS is signed updates. They're still vulnerable to the rest of vulnerabilities, but they sign it, and the sign switch is enabled over the tools. So our heuristics was not super precise here as well, but many system is vulnerable, and all of them probably vulnerable to some of the vulnerability from these three. ASRock, interesting one, it's vulnerable to 2 out of 3, same as ASUS. They make not signature check, they make something like a checksum check, which you can sort of fix and deliver the malicious BIOS update. So that was the research related how we can use the scale analysis to find vulnerabilities in UEFI-based BIOSes based on the BIOS update. But what else we can do with all of these images? We can also use it for defense. So we can basically create sort of a whitelist of the hashes for all of these images and compare every new system with this whitelist and see, okay, how many components I already have in my whitelist. And depends on this, you can find implants, you can make a deep investigation of the system. So we built a whitelist, we collected hashes. This hashes is not the simple hashes. This is Authenticode Hashes when we mask it timestamp because we don't need, to increase the coverage for our hashes. We used some open source tool to collect these hashes. That's the result, what exactly we masked in the binary. So as a result, we got about 1 million hashes from all of that BIOS images. These hashes for components of the BIOS, these components that call it UEFI or Dixie drivers, that's basically sort of small executables, which is minimum component in the BIOS architecture. So then, after we run this test for some of the system, we find interesting result. For example, I showed this last year. That's actually, this slide was the beginning of entire this research. So my old laptop doesn't have one module from the whitelist, and that was interesting result and demonstrate us that the vendor doesn't publish all of the BIOS which they're delivering on the system. So whatever was flashed during the supply chain, you cannot verify it because whatever you will see in the vendor website, they are not match. That's something which is basically industry need to work together to make sure that the vendors at least publish hashes on every single binary which they have flashed in the supply chain. That will give us the opportunities to verify the platform integrity of the system. What else we can do with these capabilities? We can detect features, if any feature is present in your BIOS. And one of the interesting features, which is basically we all want to know, is Computrace. Computrace is basically some third-party software which is injected to your BIOS to make anti-theft technology. And that software communicates with some of the OS-level components which you don't know about. So I would recommend, I'm disabling this technology if I have any laptop with this because it's pretty scary that something injected to the BIOS which not BIOS vendor doesn't know about much about internal stuff. Also, it communicates to the operation system level. So yeah, pretty interesting feature. The way how we detect this feature, we just detect for the name of the Computrace in all of the Dixie and PI drivers, and then we find around 7,000 images which contain this technology, meaning that this feature present in many systems across all of the vendors, and some of them, the good vendors, show up in a BIOS setup screen how to disable it. Some of them may not even show up. So that's a good to know, do you have this feature or not. There's a bunch of things which can be improved. As I mentioned, we have false positive, false negative. There is a list of things which we can improve it. As a conclusion, we analyzed a bunch of images. There's still a bunch of them is vulnerable to the classical vulnerabilities related to more than 5,000 different models from 9 different vendors. And what this means is all of this platform can be easily implanted or bricked, meaning that attackers with the physical access or during supply chain or during software over ring 0 can install something really persistent in your firmware which will live forever. There is a bunch of things which can be improved in our static analysis, including going deep inside each binary and check vulnerabilities like thin pawn, vulnerable SMI handlers, and so on for the future, as a future research. With this, I'm done. Anyone has questions?